Okay, I think it's in recording now.
All right, awesome.
Sure. Yeah, just a quick question, like how many of you have used the language models, ChatGPT stuff? Everyone. Yeah, okay. But like how many of you are familiar with its architecture? No. Okay. Okay. You do? What's your name? Zach? Okay. A master student here. Okay, nice.
We learned that then a few projects about modifying Google T5 and transformers.
Yeah.
So I do understand the concept.
A little. Okay. So and what about you two? No, okay. You're both undergrads here. Okay. First semester and we're the same. Okay. Yeah. Nice. Yeah. Let me know if I should start now or are we waiting for more people or?
I think we can start. Yeah.
Okay. Yeah. Sure. Yeah, so feel free to stop me if you have any questions. So we don't have a lot of people here, so it's actually very nice. Feel free to let me know if you say you cannot follow or if you need more explanation or anything. Okay, yeah. So yeah, so very nice to meet you. I'm Ziyu. I'm a assistant professor in the computer science department. So my group have been working on different like language model topics. So we build language models for applications like education. We also build language models for some like general machine intelligence problems like reasoning, planning. And my student also work on web agents. Like it's like you can deploy agents to navigate on a web and do some tasks for you. Say if you want an agent to buy something from Amazon, right? And you might be too lazy to do that, or maybe it's say your grandpa who might be too old to understand all of those buttons on the fancy website, then you might want an agent to help you, right? So we have been working on that as well. So today I would talk about more on the interpretability side of the research in my group. Yeah, I'm sure that here you're all like very familiar with like different kinds of language models. So the typical way how people try to understand if a language model works or not is by creating different benchmark data sets. So for example, this is a table that I grabbed from Meta's Llama 3.1's blog post. You're welcome. So basically these days, whenever a company releases a new language model, they will try to evaluate the language model on a set of data sets. And those data sets could cover different kinds of capabilities. For example, some general language understanding capabilities, or coding, or math reasoning, or common sense reasoning, or tool use, and there could be many other aspects that people want to evaluate, and then they try to compare the model that they released with the earlier models on the same benchmark data sets. And the numbers here are all like the larger the better. They are like some accuracy or different kinds of metrics. So people have been doing that and have been building more and more such benchmark data sets to help people understand how well a language model can do on a certain kind of task or not. But the problem is those numbers do not bring a lot of information to us, right? So for example, we see that the Llama 3 model, the 8 billion model, it seems to have a really good performance on one of the benchmark here, or it also shows to be very strong, pretty strong on the math reasoning data set called GSM-8K here. But the problem is by looking at those numbers, we still do not understand why those language models can navigate those tasks, right? And the more important thing is when those language models succeed in the task, do they succeed for the right reasons, or are they playing some tricks, right? So of course we hope that language models can have a more like generalized and like reasonable proper strategies in navigating those tasks rather than just playing some tricks. And then similarly, if we observe that, say, a language model couldn't do well on some of the tasks, by looking at the numbers, we still couldn't understand like what happens under the hood, right? So those will be the problems we want to address, and they are very important problems, especially in today. We have large language models everywhere, and everyone is talking about AI safety, talking about like how AI, how humans should build like different levels of trust in the AI models, but without a clear understanding of the inside of the language models, we will not be able to make any informed decisions. So my group have been working on the interpretation of language models. So just to give people the background, so when we try to interpret a model, there are generally like two ways, right? The first kind of interpretability work we'll do is called the behavioral interpretability. So what I mean is that, say, you have a model that you try to understand, right? And then you send the input to the model, you observe the output from the model, right? And then what people have been doing is like, let's perturb the input, right? Say if I send an image to a certain model, let me just like revise one pixel in this image, and then let's observe how the model will react to this perturbation on the input side, right? And then by comparing the different outputs on the different perturbations, we might be able to understand, okay, say this model might be very sensitive to this kind of features in the input side, right? So this is something called the behavioral interpretability, as it allows us to understand the behaviors of the models. But the problem with this kind of research is that we are still treating the model as a black box, right? So on the other dimension, which is also the line of research that my group has been doing, we are looking at mechanistic interpretability, right? So in contrast to behavioral interpretability, in mechanistic interpretability, we really want to open the black box, right? We want to look at the internals of the language model. We want to see, okay, how are the different neurons are connected? How are the features being extracted from the inputs? And how are the features being sent and transferred to the upper levels, such that eventually the model is able to implement a certain function, right? So this will be the more helpful way for us to really understand what's happening to these models, so that later on we can fix some of the like any potential problems with this model. Okay, so far so good. Okay, cool. So in my talk today, I'll give you two examples of how we have been applying mechanistic interpretability to language models. So in the first example, we'll focus more on the task when the language model fails. So this is a task, very straightforward task called syntactic code completion. And we want to understand like why the model will fail in this task. And we also hope to see that if we understand why it fails, can we improve this model, right? And then in the second example, we'll switch to arithmetic reasoning. And again, this is like, well, I call it reasoning, but as I will show, we'll basically talking about very straightforward arithmetic expression calculation problems. So language models these days can do pretty well on such tasks, but we want to understand whether they succeed for the right reason, or are they playing some tricks to get a good result on the benchmark. So those will be the two examples I will give today. Okay, so for the first one, so code generation, I heard like, for example, Arman has been using language models to generate code. And I believe like many of other students here, you might have been using ChatGPT to generate code. But okay, so to clarify, it's unethical if you do that in your homework without the permission of your instructor, okay? No. Great. So yeah, so code generation is something really popular these days, and it is such a fascinating topic because it's so challenging, right? If you imagine how you write a code, right? You want your code to be syntactically correct, and in the meantime being semantically reasonable, right? Because you want a code to implement something that you really want to achieve, right? So this is very challenging. And this year's, because of the advancement of large language models, we are seeing like better and better performance of those models on code generation tasks. And there have been like different kinds of language models specifically designed to generate code. Like Codex is like the earliest version of ChatGPT from OpenAI, but there are also like CodeLlama, right, which is a product from the Meta company, right? And there are also like DeepSeek Coder from the DeepSeek company. And you might have also heard about like how the language model agents have been built to do some software engineering task. So if you are not familiar with this, I think this can be the super cool topic for you to look into. But basically, it's like when you're using the code editor to write code, right? Then you can deploy a language model agent on your code editor. You give your agents access to your entire file folder, all of your code, right? Any data there. And then you just tell the agent like what you want to implement, right? And then the agent will read your file and generate code, and it might even be able to fix any like bugs in your previous implementation, right? So this is really cool. And yeah, we have been working on this topic for many years as well, and that's the reason why I picked this task. But surprisingly, people recently find out that even the best performing language models still failed in very, very straightforward syntactic code completion problem. What I mean is that, for example, if you are given, if the model is given a line of code like this, and say we just give the line of code up to like n+1 here, okay? And then we ask the model to complete the code, right? So this is a Python statement, right? Because we have like 3 left parentheses, right? How many? 4, right? Sorry, 4 left parentheses. So we actually want the model to generate 4 right parentheses. So we have a balanced parentheses in the statement, right? But surprisingly, even for models like GPT-4, GPT-3.5, they still have like a slight portion of mistakes on such problems. So this is very surprising. And if we are considering those open source language models like Llama, the Llama 3 model, which is the latest model from the Meta company, right? It's the potential, the possibility for this model to make such mistakes will be even higher, right? So this is very surprising. So then we decided to look into the details of this problem, and we design a synthetic benchmark like this. And the idea is the same, right? Very straightforward. Let's say we have a comment like print the string, say number 5, right? And then I just say, okay, print left parentheses number 5, and then I ask the language model to complete this line of code. So ideally, it should generate like 1 right parentheses, right? And similarly, if I just add more like string functions inside the print function, right? Then I expect the language model to generate the corresponding correct number of closing parentheses. So the parentheses will be kept balanced, right? So we design such a benchmark. Before I talk about the result, one interesting thing that I want to mention is that the way that language model completes or generate that parentheses, it's very different from how humans generate the parentheses, right? So for humans, you might write the 2 parentheses one by one, right? But to a language model, the 2 right parentheses together is 1 single unit, right? So and if you have like more than basically like 4 closing parentheses, say here you want a language model to generate 5, it will generate 2 and then 3, right? So this is very counterintuitive, and I think this is not like this does not scale up, and it's a problem with the current language model, right? Because somehow, yeah, good.
Do the colors mean something?
Oh yeah, like the color is like the way how the language model tokenize the inputs. Yeah. So basically, when language model process any inputs, the first thing it will do is to tokenize the input into different semantic units or different units, sometimes without any semantic meaning, right? And every unit will be mapped to a representation in the neural network space, and then the language model will do some calculation on top, right? But this is like the fundamental parts of the text processing, right? Go ahead.
How does the language model decide how to tokenize it typically?
Yeah, that's a good question. So people, so for the current practice, right? People typically build the tokenizer separately from the language model. And they build the tokenizer based on some statistic information. Say if they grab a lot of text from the web, right? And then they just count, for example, how frequent you will see number one, how frequent you will see like two closing parentheses together, and then they try to group those frequent adjacent tokens together into one single unit, and this will eventually give the tokenization results. But as you can see, it does not guarantee any semantic meaning. Yeah. Good. Okay. Now, okay, now that we understand like how the language model process this this kind of input, right? Let's look at the results. So on the left, I list like 7 different language models. So the GPT-2 small model is the smallest model here. But meanwhile, we also have like Llama 2, which is a 7 billion model, like 7 billion model parameters here, right? And Llama also has like 7 billions of model parameters. Pythia has around 7 billion as well. So we see that on the first 2 subtasks, they are relatively simpler. So the models can generally do very well on those tasks. But starting from the third task, when you want a model to generate like 3 closing parentheses, you see that, okay, some models started to fail on the task. And if we move on to the 4 parentheses subtask, it's the most challenging one here. You see like most models cannot do that, including the 7 billion Llama 2 model, right? For the Llama model, so Llama is the Llama model particularly tuned to generate code. The performance is much better, but remember this is a very, very straightforward problem, right? I think any maybe high school student learning programming, right, can do very well. But surprisingly, this model still have like a more than 10% gap in this task. Go ahead.
The difference in possibly function models, is that like a dimensionality kind of difference? Where they like it's embedded, or do we not know anything about dimensionality?
I don't think that's a problem with the dimension curves, because actually you see that the larger models will have a better performance than the smaller models. So yeah, so why they do not work well, that's something we try to understand in this work. I hope I will answer your question in the next few pages. Yeah. Okay. Now we're going to go to the why parts. So let me first present the findings here, right? So by doing some analysis, we find out that language models actually utilize an ensemble of mechanisms with varying levels of reliability to make prediction, right? So this is very surprising because, for example, for this closing parentheses, the balanced parentheses generation task, we think this is such a straightforward problem, right? But internally, language model actually rely on a mixture of mechanisms to do this task. And some of the mechanisms work well, some of the mechanisms do not work well. And the final prediction that we observe from the language model is like the result after those mechanisms, battle with each other, right? And another interesting thing we find was that when we see that the language model cannot do well in a certain task, it may not necessarily mean that the language model internally do not have a sound mechanism to do the task. It's also possibly because that there are so many faulty mechanisms that overshadow those sound mechanisms. right? So again, it's because like language model have like so many different mechanisms that like conflict with each other, and eventually maybe the sound one will stand out, or maybe the faulty ones will stand out, right? Which explain the final result. But internally, it doesn't mean that the language model do not have good mechanisms when we observe that it failed in a certain task, right? So that's the takeaway from our study. But how do we do that? So yeah, there will be a little math here, but basically this is the architecture of the current transformer-based language models. And as we said, like in the input side, we'll first tokenize the input into a sequence of tokens, right? And then we'll map it to some representations. And those representations will be processed progressively into the last layer. So all of the language models these days have multiple layers, right? Like 32 layers or even more than 100 layers. And this is the way how language models work, right? And at a high level, it's like every time between every two layers, the language model is trying to build a better representation of the input, right? Such that eventually it can do well in this task. And these representations are also implemented by these two components within each layer. So the multi-head attention is just a mechanism for the model to understand like which part of the inputs is important for us to model the semantic meaning of the current token. And then feed forward is just like another components to further distill the helpful information from the token, right? Yeah, so there will be some math here, but not a lot. But you do not need to understand all of them. But basically, attention, yeah, as we said, is something that allows the model to transfer information. Okay, and then the feed forward layer is something that allows the model to retrieve the information it has computed at the bottom layers. Okay.
For future instruction.
Yeah, for also like retrieving the information from its parameters. Yeah, so yeah, so these are like two major components inside any transformer-based language models these days, right? And attention is for transferring information, and then the feed forward layer is for like further computing the information and send the information to the upper level. And in the meantime, you also try to retrieve the information from its own parameters. Remember, for example, like for the llama model, it might have like 7 billion of parameters, right? And all of those parameters have been trained to memorize some kind of knowledge from the web, right? And then the feed forward layer helps the model to locate the helpful information and retrieve the information for the task computation. So that's like the general idea about like how a language model works internally. Okay. Well, okay, so going back to our goal here, right? We are trying to understand like why the language model couldn't do well in this very straightforward closing parentheses task. And the way we do this is by first decomposing the language model's prediction and attributing them into the prediction of individual language model components, right? Such as the attention, the predictions from the attention head and the prediction from the feed forward neurons. So we can do this because of this addictive formulation, right? Because as we said, every time in every layer, the language model just tries to update its representation about the current inputs, right? And the way it updates this is by calculating the representation from the attention and calculating the representation from the feed forward layer, right? So when we try to understand why the model doesn't learn a good representation, we can accordingly go back to decompose this representation into the representation of the attention and the representation from the feed forward layer, right? So that's a rough idea. And no worries if you feel like this part may be too like difficult or too mathematical, but yeah, the basic idea is that we are trying to understand, say, when a language model couldn't do this task well, is it because it doesn't have good attention heads, or maybe it doesn't have good feed forward neurons, or maybe it actually has good attention heads and good feed-forward neurons, right? So that's how we try to answer this question. Okay. Okay. So we try to once we have this decomposed formulation, we try to understand, like, do we have good attention heads or do we have good feed-forward neurons? And the way we do this is by directly using the representations from each of those components to make a prediction, and we can simply report the task accuracy, right? And by doing that, we actually see something very interesting. So here we present the attention heads accuracy distribution for two different models, the GPT-2 model and the Code Llama model. And what we've shown here is a histogram of the attention head's accuracy, right? That means we directly use the attention head to do this task. So first of all, we can see that for all of the models on all of the 4 different subtasks here, right? We always have highly accurate attention heads in the model, right? So like 1.0 accuracy, right? And that's very interesting because, for example, if you still remember for the GPT-2 XL model, the model has 0 accuracy on the 3-paren and the 4-paren subtasks. But internally, we see that the model has very accurate, like 100% accurate attention heads, right? And that's why we believe that the language model is making a prediction by aggregating the predictions from different components, right? And we also, I'll skip some of details here, but we also find that for all of those models, no matter if they have good or bad performance on these tasks, we can find attention heads that can do well in all of the 4 different subtasks. So we call them the generalized components or generalized mechanisms. And this is, again, very surprising, especially for the GPT-2 XL model, which has only 0% accuracy on some of the tasks. Yeah, so we further look at attention pattern, right? So as I said, in the language model, attention is a mechanism for us, for the model to transfer information, right? And here we're using the different intensity of the color to indicate how strong the attention is from the output to the input tokens. And here we see that for this particular attention head, it always attended to the init function, like the print function here or the string in the other 2 subtasks. And this is the same for this attention head in the GPT-2 model as well. So for both of them, those 2 heads, they are very generalizable, and they also show like very clear attention patterns. But for the last head here, it's not a generalizable head, and we do not see very clear attention pattern, right? So takeaway here is that language models internally do develop like very good mechanisms, and for those good mechanisms, especially when we think about the attention heads being the thing that implement the mechanism, we see that those heads generally have like very clear pattern in terms of the attention distribution or how they transfer the information to the output prediction. Okay.
You mentioned, how do you measure the attention accuracy? Just check.
Yeah. So let me go back to the yeah, I kind of skip some details here, but basically, so when the language model update the representation, like the neural representation of the inputs, right? It update that layer by layer, right? But internally, it's like you will first send the representation from your input token to the multi-head attention, and the multi-head attention will also calculate a representation for you, right? Then the way we can get we can measure the task accuracy for this attention head is by directly using the representation at this position to do the prediction, right? So typically we use the representation from the final layer to do the prediction, but we can actually use the representation from the individual components inside the transformer to do this. Okay. Right.
How do you do that closed source model?
Yeah, great question. So far we are all using open source models. Yeah, that's a big constraint here. Yeah.
Even GPT-2.
It's open.
Oh,
I mean, OpenAI initially was a real open AI, but after GPT-3, I mean, let me see. Yeah, okay, GPT-3 actually has different versions, smaller versions and a large version. And when people typically talk about GPT-3, they are referring to the 175 billion parameter version of GPT-3. That one is not open, but the smaller versions are actually open. And yeah, starting from from that, it closed the AI. So yeah, yeah, that's a good catch. And that's actually a practical concern about this community, because yeah, if the models are not open, we have no way to interpret that. And then the next question is, if we have, say, we have the GPT-2 model, right? And if we can get some insights by interpreting the GPT-2 model, then can those insights apply to the larger models that are not open to us, right? So this is like the generalization of the insights from the open model to the closed model, but it's still like a very open question. 2018. Yeah, many years ago. Yeah. Yeah, I think Meta did pretty well in releasing the Llama models. They are all like open sourced. All right. Okay. I also skipped some other details, but basically we have done the same to understand the task accuracy of the feed-forward neurons, but we do not see them to be very helpful. And we also have some studies to understand like why they are not helpful. I can just explain the result here. So basically feed-forward neurons works in a very different way compared to attention, right? So attention is used to transfer information. It's very scalable, right? If you have a very long inputs, then by leveraging the attention mechanism, you'll be able to transfer any information that you find helpful to the prediction precision, right? It's very scalable. But the feed-forward neurons, they are not scalable. And feed-forward neurons are typically considered as the memory of the language model, right? And you can either retrieve the information from your memory or not, right? You only have two choices. So it's like the binary, we call it the binary activation, right? Either you want to retrieve this knowledge or you don't want it, right? But the problem is in our real life, there are a lot of problems. They are not binary, right? Say when we think about text classification, topic classification, there are so many different topics, right? If we rely on the memory to figure out the topic, it'll be very challenging because either you retrieve this topic or not, right? So because of that, feed-forward neurons have this intrinsic constraint in its architecture. It will never generalize beyond two subtasks. So in our context, it's like either it will promote like out of the four different closing parentheses we are considering here, right? Either it will promote one of them and suppress all of them, or the other way around, right? It could also like promote all of the other three, but suppress the first one, right? But there's no way for the feed-forward neurons to smartly control, to say, okay, I only want to promote one of the three rather than all of the three altogether. So there's no way for the neuron to do this. So yeah. Okay. And there's also something we discovered, and we call that the noisy promotion. What it means is that like those feed-forward neurons, they are not able to give us like very precise result or very precise prediction but instead, when they think that, say, the third, like 3 closing parentheses here is the correct one, they will try to promote all of the 3 choices here because they cannot pick only one of them up. So that's a problem. Okay, so a quick summary so far, right? So we see that the language models do not do well in this task, and we try to understand that by first decomposing the language model's internal mechanisms into a set of mechanisms driven by the attention heads or the feed-forward neurons, and we see that even when the language model fail in a certain task, internally it has still like developed like very accurate mechanisms or say very accurate attention heads, right? So how is this be useful, right? So one thing we can do is that, say, if we are able to rank different components, say different attention heads, based on how useful they are or how accurate they are, right? Then we can do something called the steering, right? Steering means that it's actually very straightforward. It just means that let's strengthen the impacts from those more reliable components, right? And in this way, we can avoid the overshadowing problem that we have just talked about. Yeah, and this is like a very, very straightforward approach. But surprisingly, we see that it works very well. So for example, the first 2 plots here, the first plot here case, this shows the accuracy on the 3' task. And on the x-axis, we're showing the number of attention heads ranked based on their reliability. And those are the heads that we steer, or in other words, like we strengthen, right? And we see that for all of the models here, even for the model initially with 0 accuracy on this task, as long as we steer the top 5 most accurate attention heads, we can immediately improve its accuracy from 0 to 100%, right? And it's the same for several other models on the more challenging 4 parentheses subtasks as well. Although in this case, sometimes we'll need to steer more than just 5. We may need to steer like top 10 most helpful attention heads. And sometimes for some models, for some reasons, which we still don't understand, we will have to steer like 60, top 60, all of the 60 attention heads, so that we can improve its accuracy from 0 to something close to 100%, right? And there is still the model, the GPT-2 small model, which this approach never works. And we think that it might be because this model is too small and internally, like it just have like too many noisy mechanisms, and simply steering the top 60 would not work. So that's something we found. And we also have experiments to steer the feed-forward neurons, but we find that it's generally not as effective as steering the attention heads. Okay, question?
Is that just overfilling the attention heads in your subplot?
Very good question. So, I mean, there's a potential that, say, we find the attention heads on these closing parentheses task, we steer that and see its improvement, then would that hurt the model's other performance, right? We actually have an experiment in the paper. We found that it doesn't hurt the general coding performance of the model. It actually improved the model. So that's another thing we find to be very interesting. Like if you find a problem, even a very small scope problem with your current model, and you fix that, and maybe this can have some consequence, like good consequence on improving other kinds of capabilities of the same model. But still, like we do not have like a systematic analysis to understand their correlation. But yeah, it's a really good question. Okay. Yeah, so that's the first work, and I know we are a little over the time, not over the time yet, but a little late on the schedule. So I can move on to talk about the second one, and I believe that one can end quickly, and then I will make sure to reserve time for Q&A if you want to ask about like how to do AI research, this kind of questions. Okay. Yeah, so for the second one, This is actually a really fun one. So again, for this one, we are trying to understand like if linked model can do well in a certain task, does it do well for the right reason? And the specific task we focus on is arithmetic reasoning. Yeah, quick question to everyone. How do you calculate this expression? No, that's too lazy. No. Okay. No, as humans, not as ChatGPT. Like, how do you solve the problem? Yeah.
Maybe get certain numbers together. So in this case, I would probably add the 42 plus the 20 to get 62 minus 15, which is 47.
Yeah.
And it could be that. I could be completely wrong.
I mean, yeah, I mean, that's a way how I will solve the problem as well. Like, do people have a different solution?
Get the find the smallest number, take 15 minus, 20 minus 15, get a really small number 5, and just get 42. That works too.
Yeah, that works too. But so one thing that like both answers share here is like we'll try to solve the problem in a compositional way, right? No matter if you want to add, solve the 42 plus 20 first or the 20 minus 15 first, right? But somehow you want to solve like one calculation, like one operation first, and then you try the other, you apply the other operation, right? So this is like a very, very natural way, like a compositional way, how humans solve this problem. And it's very elegant, also very generalizable in terms of, say, if I add another operation after minus 15, I believe everyone can solve that, right? You just keep applying the operation one by one, right? So linked models have show like pretty good performance on such tasks. And here, I'll just show the result using the Llama 3 8 billion model. And for example, for the task like A plus B plus C, right? The model can have an accuracy close to 100. And the model actually have like pretty good result on most settings, except the third one. For some reasons, it couldn't understand, it couldn't calculate like A minus B plus C, right? And this is very strange, right? Because based on our if the model does the calculation in the same compositional way as humans, right, then it doesn't make sense because this is not much different compared to the other equations, right? So we want to understand how exactly the language models solve such arithmetic calculation, right? So again, I will just present the result here immediately. So the takeaway is that linked models do not follow the same compositional ways as humans in solving such like at least the 3 operand arithmetic expression problems. And what it does is like okay, I'm showing the diagram of a linked model. So this side is the inputs, this side is the output. Okay, and so the 4 different circles here are like the, say, A plus B equals something like that, right? The different inputs that you send to the linked model. And as we said, the linked model have like multiple layers of calculation. And in the end, we'll grab the representation from the last layer and from the last token position to make a prediction, right? So this is just an illustration of how linked model is used for this task. Okay, so what we find is that, first of all, maybe because the task is too simple, the linked model actually waste like almost half of the total layers doing nothing, right? So it's like it's not actually calculating any operation, and it's calculating very generic semantic understanding about this task, but nothing specifically about this operation, about any operations in the expression. And then suddenly we see that the language model will transfer the information from all of the operators and the operands immediately to the last token position, right? And typically this is like the equal sign, right? So it transfers all of the information here. And after that, the model completes both operations altogether in the last token position, right? So there's no composition being observed here, right? And this is very interesting because it might allow us to explain a lot of things, right? For example, why when the model understand how to calculate a plus b and a minus b, then why it still couldn't understand how to calculate like a minus b plus c, right? Because internally it does not have a compositional or generalizable mechanism in doing this kind of calculation. Okay. Yeah, and we term such the subgraph that we find out as the all for one subgraph, because eventually the model just transfer all information and complete all of the calculations in the last token position. Okay. I'm going to skip some details here, but I'm happy to share the slides with you if you are interested. But yeah, this is a cool result, the final result I want to show. So basically we find that with such a simplified subgraph, we can actually recover the models, like the full model's performance pretty precisely, except for the one with the low accuracy itself. It might be because the model internally does not have a clear mechanism in completing this calculation. So eventually our subgraph cannot recover the same calculation, the same model performance either. But otherwise, the faithfulness score of this subgraph in terms of recovering the full model's performance is pretty high. And we also have some experiments try to understand like what attention heads are critical for the information transfer. And as we expect, those important attention heads, they are basically transferring information from the three different operands to the last token position for the yeah, and then complete the task. Yeah, so yeah, I finished the second one very quickly, but yeah, that's roughly what I wanted to present today. I hope people are still following me. That's okay. Okay.
Nice.
Thank you.
Thank you so much.
Thank you.
Sure. Yeah, I'm happy to answer any questions about the work here or general AI research or anything you want to chat about. Yeah.
So I know we had a little bit of a discussion on like closed source and open source models. So I guess I was curious, what's your take on that? Do you think that it would be better to it would be better overall to keep some open source, or is there some drawbacks to that? Like, I guess like what if you had to explain like why should companies keep models open source, and then why should companies keep it closed source? Both perspectives.
Yeah, that's a good question, and it's not an easy question. So I mean, there are some companies which justify the purpose of keeping all models closed by saying that if you open a model and you do not have a clear way to protect those models, then the models might be exploited by some malicious parties. And but I mean, who knows if they really think in that way. Like some people also say that it could be that those companies they are trying to they want to increase their profits, right? So if say OpenAI release all of the GPT models to the public, then how can they earn money? So yeah. But I mean, as researchers, we definitely hope that we can open source everything for science, right? Yeah. Go ahead.
The slide about you talking about like the model just wait for half of the layer and then transfer all information to the last token. What was supposed to be the good composition, like what you were talking about? What was the good expectation?
Yeah, so if the model is actually doing the calculation in a compositional way, then we'll expect that the model will use, say, the first few layers to calculate. Actually, let me see if I can draw here. Say if you have like 1 plus 2, and then minus 4, okay, and then equals, right? So if the model is solving this equation compositionally, then we expect that it will use some of the first layers to complete 1 plus 2, and somewhere we should be able to see an answer 3, in the same way as how we measure the task accuracy in the previous work, right? You just grab the representation here and you use that to make a prediction. It should give us 3, right? And after that, maybe these 3 will be used in by the later layers, and eventually here we can calculate like we got like -1 as the output, right? So that would be the ideal compositional way, but we do not observe that.
So I was just curious, do you think that, I guess with AI being able to do a lot of programming tasks, do you think that it'll come to a point where it can create novel research?
Yeah, that's a very good question. And I don't know if you guys are familiar with the concept of AI for science. So this is like a really hot topic these days. And what people are trying to do is exactly like what you said, like they try to use language models to discover new science. For example, there are so many difficult problems in mathematics, then can we use language model to solve them, or at least help the scientist in solving them? I remember there was an article from where DeepMind or somewhere else. I don't quite remember, but they find that they prove how they use language model to solve a very classic math problem, and the country, United States, for example, like the NSF, like National Science Foundation, it has a recent call for proposals exactly on the same topic, like can you use the current AI to accelerate mathematics? So this is one example, but otherwise people have also been working on, say, using AI to discover like molecules or I don't know, genes or different things. I'm not super familiar with them, but yeah, people are very interested in that. But to me, the challenge is, say, we train the language models on the data that human provided, right? That how much can the language model go beyond the human intuition, right? How creative can language model be if they learn from the human data? And another concern is also that these days we have so many different AI models, and people are now writing documents or like generating videos, images, or using AI products that maybe for the next 10 years, most of the data that we can collect on the web for training the next version of GPT models might be generated by the older version of GPTs themselves, right? Then there will be this loop, right? Then how likely can the model actually think about something outside its own capability? So, yeah.
So follow up to that, what, do you think that, like, how far away from artificial general intelligence do you think we are? Do you think there's gonna be like a different model altogether? And I guess like what's like the stepping stones to get to AGI? Do you think it's achievable?
Yeah, I think this question will be too big to answer. But the sub question you have, like, are we going to always use, say, the transformer-based language model architecture? I mean, it's not sure, because as more and more people work on interpretability, we have seen like all kinds of like drawbacks or limitations of the current language models. And there are actually a lot of doubts about whether we should keep using this architecture or should we do something else. And this is exactly like one example, right? Even for this simple task, the model cannot have a sustainable or generalizable way to solve it. Then do we really want to rely on such a model, or do we really believe that such a model can do more complicated problems? So,
questions.
Yeah.
Like for the code generation task, the model is just using the same model as any other, no secret sauce or
You
is there any special components or just
you mean the say the you mean the GPT models that are not open, or
let's say I have a model that's used for text summarization, for example, just a large language model. And that same model with the same architecture can do code generation or do
I see.
special.
So I mean, I think you can use the same say GPT model to do different tasks, and that's actually the motivation for people, at least the initial motivation for people to develop such a large language model, because we are very lazy, right? We do not want to build one specialized model for each task. We want one single model that can do well in any task. But it is actually true that a lot of closed models we are using these days, they are not just a language model. They have some other components. For example, GPT models have been said to also have an external verifier. That is like you ask the model to do some tasks, but they also need to have a verifier to check the correctness of the output or the safety of the output or many other things, and before it returns the answer to you. So today's the language models are not just a language model.
The basic of it is
Yeah.
the model can generate code,
Yeah.
like how you translate from one language.
So translate language, or sorry.
Just the model can generate code by itself.
Yes. Yeah, go ahead.
So a lot of models have like reasoning that. Is that connected to like specific like any scientific computing hardware, or is that like what is that reasoning?
The reasoning mode. Okay. So first of all, we do not know how OpenAI implement this reasoning mode because it's closed. But have you guys heard about the DeepSeek models? So it's the first reasoning models that is open sourced. Okay, so DeepSeek achieved this by first of all, like having good data sources, right? It's like if you want to train a model to reason for long, then you need to have the corresponding training data to teach it how to reason for long. Okay, and the second thing is DeepSeek relies on reinforcement learning. So reinforcement learning is a kind of learning approach where the model will improve itself based on the final reward. It's like I give you a task. If you do well in the end, then you'll receive a high reward. If you fail, then you'll receive a negative reward. So, and then we train the model to plan for how it wants to answer these questions such that eventually it can earn a high reward, right? So that's reinforcement learning. And in the DeepSeek, researchers found that when we train a model with reinforcement learning, we can actually discover what they call the aha moments. It's like initially the model only think for shots, but as we keep training the model on more and more challenging problems using reinforcement learning, they find that the model itself learns how to think deeper, and sometimes the model even backtrace. They will say, okay, wait, I don't think that is right. So let me think again, right? And then you go back to the initial point and try to think the other way of solving the same problem. And people find that models can naturally develop this long reasoning process. Yeah.
Is that, so if I run like a complicated reasoning task on like DeepSeek, well, does that improve the model itself, or does that instantiation?
I see. Yeah. So for the training, you do need to update the model's parameters. But yeah, it's actually a really good question. Like these days, there's also the very important topic called inference time computation. So we train a model, and when we use the model, we do the inference, right? Inference just means that you just run the model on a certain task. And people are also working on, say, if you have already trained a model, you're not going to change the model anymore, then how can you prompt the model in the right way such that it can think for long, it can solve the more complicated problem. And this process often involves a long sequence of thinking, a long process of thinking, and which increases the inference time. So people call that like the inference time problem solving kind of. Yeah, so I hope that answers your question.
Yeah. In that case, that is just an association of.
Yeah, like an existing model. Yeah, yeah. But I mean, like, typically you still need to update the models such that it has the capacity to think for long. Yeah.
Okay.
Yeah. And yeah, there are also people working on balancing between short and a long thinking. I don't know if you guys have tried this before, like when the OpenAI's reasoning models was first released, when you say hello, you might need to think for a minute to say hello, right? Then yeah, that doesn't make sense, right? Then when should the model think for long and when should the model give you a direct response, right? So that's, yeah.
To add on to that, I don't know what's the right term to that, but there's something called soft update and hard update. Like if you just prompt it well, and like even like me as a user, I just use ChatGPT and say keep on reasoning with it, and I kind of improve my prompts. So it's kind of like a soft update to it. But from the OpenAI perspective, if they want to change the parameters, so that's kind of like a hard update.
Yeah,
So
yeah.
it's like soft update and a hard update, but I don't know like what are the right terms with this, but yeah.
Yeah. I think both are the common practices these days. Yeah.
Okay, so one last question I have, like what inspired you, what got you into research on this language model space?
Oh, it's fun, right? So yeah, it's interesting. I mean, like I when I my bachelor degree was not in computer science. It was in something relevant related to double E. I learned a lot about like signal processing at that time. But yeah, I think I'm more interested in machine learning stuff. So I switched to computer science and started to work on some machine learning projects as I came to the US and then the PhD. So yeah, and this topic is it's a really cool one. Yeah. But I mean, I feel I'm also lucky, like luckily working on the most popular topic these days.
So that you know everyone's having fun with this topic if it's the most popular.
Yeah. Okay.
Sorry, I'm tired, but
Yeah, sure. Let me stop the recording first.